So yesterday we were looking at the introduction to compute virtualization, and I'm going to just peruse through these slides. We said that in this chapter we're going to Cloud Computing 1.0 focuses on virtualization, which is today the foundation of cloud computing. We looked at some of these objectives, and in this lecture today we want to understand what KVM technology is, and we looked at the introduction to virtualization, though we did not complete it. I think we're going to continue. We looked at what the virtual machine is. We also went through what virtualization is, the brief history of virtualization, important concepts in compute virtualization, where I looked at the guest operating system, the guest machine, hypervisor, host operating system, and host operating system, and the host machine. I would very much love to give you the permissions to record, but unfortunately or fortunately, I don't know, but this meeting is controlled right from China. If you notice, it's from WeLink Zoom, which is from China, and they have some of the permissions, and I am unable. That's why sometimes we get to a point when I have to mute someone and I am still requesting for host permissions from all the way from China. So but it's something that I'm going to suggest, so that they can be able to give you permissions to record, and then maybe the coming other lectures you'll be able to record. However, I record and share the classes via the Telegram channel, so you can always download it or watch it from there, depending on what works best for you. Okay. All right. So I hope I've answered that. Sorry. All right. All right. Okay. So the important concepts. Okay. I'm going to make a slideshow. Okay, so we looked at the guest operating system and all these other concepts in virtualization. We also looked at the different types of virtualization hypervisors. Okay, Ogwanga, are you saying something? Okay. So we looked at type 1 and type 2. We also said that type 1 is also sometimes referred to as bare metal. Before I proceed, I emphasize that attendance is key. Kindly make sure that you sign those attendances, and also that you're part of this call. And when you leave and you know there's a reason why you can't be available or why you can't attend, kindly communicate via email, because what happens is that someone takes random screenshots of the participants in the chat, and also someone will go through the attendance lists that we take every day. So kindly, I emphasize attendance is key for these online courses. Make sure that you attend, and you attend in person. Okay, we have hosted virtualization, which we also called type 2. The difference is that, like you hear the word bare metal, type 1 is installed directly on top of the hardware resources, while hosted or type 2, you need an operating system, and then you install the hypervisor inside that operating system, which has other applications running, and then you can now set up your virtual machines. Okay, so can I request we can hear, maybe you didn't join the class with your device audio. Okay, I'm going to focus on the chat now, because it's somehow interrupting me, but let me focus on what I'm presenting now. So we also looked at the characteristics of virtualization, and we looked at partition, we looked at isolated as well, we looked at encapsulated, and also we looked at independent. All these things are available in your notes. Kindly take off some time and read through them, try to understand them in detail. So we stopped at this particular topic where we're going to be looking at the CPU virtualization. Remember, in compute, we are looking at compute virtualization, the major compute resources that we are talking about yesterday. We have our CPU, which is a processor. We have our memory. And also we have our input and output devices. And putting together all this, we come up with a computing power. For you to be able to have a computer or to have computing power, you need a processor, you need memory somewhere, and then you need input and output devices. Okay, I remember sometime back in high school, when what is a computer and you define it, it is an electronic device that is capable of processing input and output, isn't it? Okay, so these are the key things when we are talking about compute virtualization that we are going to look at. We're going to look at how do we virtualize our CPU so that we can make it appear that we can make our virtual machines believe that they have their own CPU, and yet it's actually either one or two, or depending on the cluster. How do we bundle them up together for use for the virtual machines? Okay. Okay. So we're also going to look at memory virtualization and also try to understand how do we virtualize our memory. And then later on, we're going to look at input and output devices, and that will sum up the compute virtualization topic. Okay. So I see in the chat Irene is having issues. Irene, have you been able to troubleshoot and get the audio? Because I don't want to leave anyone behind. Irene? You could just maybe post a message in the chat. Kindly let us know if you need help, and we see how best we can help you. Okay, all right. So let us look at CPU virtualization. I assume all of us know what the CPU is, okay? And what it is used for in a computer. So now I want to know, how can we virtualize this computing power? And we already said that compute virtualization includes CPU virtualization, memory virtualization, and also how we can virtualize our input and output devices. But there's something very important when it comes to the CPU architecture and when it comes to the way it handles and passes on instructions. We are having what we are calling the protection rings, ring 3, ring 2, ring 1, and ring 0, okay? Or sometimes we refer to it as the hierarchical protection domains of the CPU, and these are basically put in place for security purposes. So there are 4 rings, this is ring 1, ring 0, ring 1, ring 2, and ring 3, which is a hierarchical control from the most to the least privileges. And what happens is that anything that is running at this ring 0, it is what has the most or the highest privileges, or which has direct access to the hardware resources. And in this case, we are talking about our CPU here. And usually this is the operating system in a normal kind of environment without virtualization. This is usually the operating system or the drivers which operate at ring 0, which usually has direct access. It has the highest privilege to access the hardware resources or the CPU. So all the instructions that are sent by the OS, which are sensitive or core, they go and they can easily manipulate the CPU or call or execute instructions or send instructions to the CPU. So generally, only the operating system, like I said, and the driver, they have this privilege. And this guy here, all our applications usually operate at ring 3. They usually operate at ring 3, which has the least privileges. And to protect our computer, the people who designed, our computer scientists who designed the CPU, thought it wise that some dangerous instructions, they should only be executed by the operating systems. Maybe the instructions will change state of the hardware to maybe delete, format, and do all those things. They should be handled by the operating system, and this helps to prevent malicious software from randomly calling hardware resources. This means that if a program needs to enable, for example, most of you have your Android devices. When you install a new application on that operating system, which is Android, and you are setting it up for the first time, and let's say you open your camera and you want to take a photo in let's say WhatsApp, and you click on the camera icon, it will ask you, you have installed WhatsApp, but we need to ask Android to give us permission through Android so that we can be able to actually access the physical camera on the computer. Do you want to allow? And then most times, actually, most of us don't read. As long as we want to use the application, we just say allow, 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 allow. Isn't it? Today's class is quiet. I don't know because it's cold or I am boring. Hey, there are no people making noise in the background. I'm trying to ask myself what happened to us.
We
I
are
am very
following.
attentive.
We are just very attentive. We don't want to miss anything.
Following.
Hello, Sam. We
All
are
right,
very active
hello.
and
At least
listening.
now I know that there are people at the end of the other end of the phone call. You know, I could be busy talking to myself when my network is off.
That's possible. But we are on. We are following closely.
All right, that is good. That is good. So, like I was saying, like when you install an application, many of you have installed an application, Snapchat, regardless of the application, and it needs to access the storage on your phone. It will ask you, do you want, and even in most cases, even on the operating system on Windows, when you're installing, just because for it asks you, the operating system asks you, the application you are going to install will need you to give it administrative right. Are you sure you want to go ahead and install this application? Yes or no? Most of the times we don't read, we just say yes. But what actually this, or the purpose or the reason for this is that because these applications run at ring 3, but now you want to make the operating system aware, which runs at ring 0, that sometimes I may need to send instructions that need me to actually directly access the operating system. So this means that the program must request ring 0 driver to do that on its behalf. In actual sense, you're requesting the operating system to actually go ahead and send that instruction to the hardware. Okay, so usually the operating system sends two types of instructions. There's what they call privileged instructions and the common instructions. Usually the privileged instructions are used to manipulate and manage key resources of, and by resources we are meaning the hardware resources, key resources, and these instructions can be executed by programs of the highest privilege, which we said it is ring 0. So, and the other type, which is common instructions, that can be executed by programs of the common privilege level, and that is ring 3. Okay, so in a virtualized environment, now which one? This one, which you're looking at, there is another special type of instructions which you're calling the sensitive instruction. Okay, which are calling the sensitive instruction. A sensitive instruction is used for changing the mode of the virtual machine, because now this is in a virtualized environment and we're having our virtual machine, have our hardware resources, we have our hypervisor, we have our guest OS, and maybe other things like, let's say, libraries can be here, and then we have our applications running at the least privileged domain, which is ring 3. Okay, so These ones, they are, when we send the sensitive instructions, they are used to change the operating mode of a virtual machine. And this instruction is usually handled by the hypervisor. So whatever instructions you send, they are handled by the hypervisor, or what we're calling the virtual machine monitor. So after a privilege instruction that originally needs to be run at ring 0, this one, in the guest always. What happens in virtualization, like I said, you are virtualizing, this guest operating system is not aware that actually it is a guest operating system. Can I please meet you, Tito and Nelson? All right. So this guest operating system is actually not aware that it is a guest operating system. As far as it's concerned, it's an operating system. And it thinks it has access to the resources which you allocated to it. It thinks they are actually physical resources that it is using. So what happens, and remember, we said operating system and usually drivers, which are also installed on top of the operating system, they operate at ring 0, and they send those privileged instructions. So what happens, this one is in guest, remember it's now operating at ring 1, but now it is sending what privileged instructions which are actually meant to be sent by the ring 0. So this guy here is trying to send privileged instructions. But remember, now this is going to reject it because for it, it only accepts privileged instructions from all applications that are running from ring 0. Okay, so that becomes a challenge. That becomes a challenge on our side. So the instruction is, they are usually handled by the hypervisor, and that originally used to be run at ring 0. But remember, now the guest operating system is deprived of that privilege since it is running at ring 1. Please don't cram. You won't find those question asking you to define the things that are running at ring 1. So please don't cram, just have an open mind about this. And usually the things I tell you, please pay attention or take note, kindly take note. There's a reason why I'm telling you to take note. So as saying, so the virtualization technology was firstly applied in IBM mainframes. And IBM mainframes, by that time, the mainframes, they used to use the reduced instruction, small set computers. Yes, they used to run run that. And by that time, how they used to emulate or virtualize, they used to use what we are calling trap and emulate. You send the instructions, they trap them and emulate, and they make this hypervisor emulates, and it makes the hardware or the CPU believe, and also the guest operating system believe that it is actually talking directly to the hardware, and yet in actual sense, it is talking to the hypervisor, where the hypervisor goes ahead and cause the hardware resources to automate on its behalf. So the CPU virtualization methods used by mainframe are depriving and also trap and emulation, which are also called classical virtualization methods. These are the basic principles that the guest operating system runs the non-privileged level, that is depriving the virtual machine, that is depriving it of the domain 0. Remember, now we are depriving it, it's running at ring 1. And now we get our hypervisor, and now we give it the highest privilege, and it is running at our domain ring 0. And this is what we are calling fully, by giving this, it is now controlling or fully controlling the hardware resources. That was okay then. But now the challenge is, as technology evolved, I remember when you studied in the history of computer, we went to mainframes, to more powerful computers and more powerful computer, until when they came to a point and they innovated or came up with commodity x86. And with this, what used to happen, it used to use CISC, and this is the complete instruction small computer or set, and this is the reduced instruction. What used to happen is that when it was using RISC, we had our instructions that were being sent. we had our privileged instructions, or what we are calling the core instructions, and inside our core instructions we had our sensitive instructions. So what this meant, that these sensitive instructions that are now being added on when we are using virtualization technology were part of the core instructions. So it was easy for this guy to trap and emulate and also use the depriving technique to deprive this operating system and to emulate so that it traps, emulates, and then it is able to pass those instructions to the CPU. But now as the world evolved, they came up with the commodity X, which was using sys, and for its architecture, we have our instructions and we have our core instructions or privileged instructions, and also we have our sensitive instructions. Now, take note of this. We have our core instructions there, but then we also have some instructions which are sensitive. These ones, which are sensitive, these are sensitive. You should take note that as we are having those sensitive instructions, but there are some sensitive instructions which are part of the privileged instructions, just like before. But then there are also other 19 instructions which were not part, or which are not part of the core instructions. So the problem will arise there. Because how can a privileged instruction sent by the guest OS of the virtual machine be performed when all the privilege of all virtual machine systems has been removed? And the trap and emulation takes effect, but when it comes to this architecture here, it is actually hard because these 19 instructions are not part of this, and we are going to have issues. So what happened now, it introduces us to the types of virtualization here. And we are seeing that these types of virtualization, we are having what we are calling full virtualization, para-virtualization. We're going to look at them in a bit. So they came up with a virtualization, and I've already explained that the CISC here, what we looked at, we are saying that 19 instructions in the CISC sets, they are based on the commodity x86 architecture, and they are not privileged instructions. So these instructions run in ring 1 user mode of the CPU, and we said already this is not a privileged ring, and therefore only things that are running inside here are the things which have the ability to send direct instructions or sensitive or privileged instructions to our CPU or our hardware resources. So this brings about a problem when we need to actually virtualize those things, and that is what we are calling virtualization vulnerability. Since the mainframe or the best CPU in this category, the methods cannot be directly translated to the 86 commodity platform, and we said because we have the 19 sensitive cases which are part of the core, or which are not part of the privileged instructions. Okay, so there it becomes a problem. So that is why the architecture, the architects or our computer science decided that, you know what, why don't we come up with full virtualization so that we take care of that problem. And now we are looking at full virtualization. We are also going to look at para-virtualization, and also later on look at what we are calling hardware assisted virtualization. So full virtualization basically, or sometimes it's also referred to as the classical, method of virtualization, but basically it is usually a method that is not suitable, like you already see its architecture, not suitable for commodity x86 processors, because the 19 sensitive instructions that I've already showed you are beyond the privileged instructions. So CPU virtualization problems are now become hard, or they become hard to be solved, and that's why they decided now to come up with para-virtualization. We're going to look at virtualization. So with full virtualization, what happens is that, you know what? When an application sends instructions from our ring 3, these ones that are not sensitive or are not privileged, let them just go directly and they're processed by the CPU. But now, if our guest operating system wants to send, because the guest operating system, remember we said it only sends privileged and common instructions. But whenever it wants to send either privileged or common instructions, it has now to send them through the hypervisor. Then the hypervisor calls the hardware resources. Now you can imagine there's some kind of bottleneck, there's some kind of hard work there, because now every time all instructions are now being sent, we are giving our hypervisor a hard time for it to process all these instructions all the time. Okay, so now this is it was a method that is not really fancy or called for. So because all operating system records sent by the virtual machines are forwarded to the hypervisor, then the hypervisor performs the translation into binary, sends to the hardware, because the hardware then receives it, and these are all instructions that are being sent to it. And these requests are now scheduled to the CPU to be at the privileged level for execution. So there is a problem there because it is stressing our hypervisor. So full virtualization here was first proposed and implemented by VMware, and it usually translated the code of virtual machine without modifying the virtual machine operating system. So this means that virtual machines had a high portability. You could actually move them from one hypervisor to another, and of course compatibility. But this translation causes performance overhead of virtual machines of the hypervisor, because now every instruction is sent, translated by the hypervisor, sent, because it's now trapping and emulating all the instructions sent by the operating system. Okay, so which means that full virtualization, when we're using virtualization, the virtual machine operating systems, they do not need to be modified, because all the instructions would be sent to the hypervisor. They are trapped, they're emulated, they call the hardware performs the instructions, sent back to the hypervisor, translation back to our guest operating system. And this guy will continue believing that he's an operating, or she's an operating system running on top of hardware, not knowing that actually they are in a virtualized environment. And also they were portable, and but the disadvantage is now modifying some of the settings or configurations became hard, and also because of the translation and emulation of at all the time, there was some kind of large performance loss and increases in this, having to come up with a very complex hypervisor. Okay, so that's why Zen decided to come up with what we are calling para-virtualization. With what we are meaning by para-virtualization, what we do, we get this operating system, we modify its source code. It's more like getting your dog and you train it that you have to do ABCD, although this is not a dog. So we get our guest operating system, modify its source code, and make it aware that you are no longer operating at ring 0. Actually, you are a guest operating system. So get that from today. You're running at ring 1. So please do not send those sensitive instructions, including the 19 sensitive instructions. Okay, just know you are a guest operating system. So you modify the source code of the guest operating system, and now you run it on top of your hypervisor. And what it does, it just needs now to make the hypercall. There's no translation, and it calls the hypervisor. Hey, hypervisor, I need to do this, and the hypervisor will do that without necessarily having to translate all the common instructions and also the privileged instructions. So virtualization vulnerability comes from the 19 cases that we have already talked about, the 19 sensitive instructions, sorry. And if you are to modify the operating system or the guest, this will avoid the virtualization vulnerability. You modify and you find a way of tweaking these 19 sensitive cases, and you tell the operating system that, you know what, please do not send including those things because you are actually a guest operating system and you need to operate or run at ring 1. So that happened that way. So what the disadvantage of this already, some of you can already see it. We all
Hello,
know.
sir. Hello.
Yes, please.
I'm trying to ask a question.
In the middle? Yes, okay, go ahead.
What operates at ring 2?
What operates at ring 2, it depends on the instruction or how that software was designed, but usually like libraries sometimes, or frameworks, things that a layer that happens just before your application layer. Okay, so you don't have to necessarily get that this must run at this ring, but usually there are libraries and frameworks, okay? Like the .NET framework of Microsoft. All right, so I was
Thank
saying,
you.
all right, you're welcome. I was saying that by making this guy aware that they are a guest operating system, okay? But we're already seeing there's a disadvantage in this. We already know how many open source operating systems do you know of that they are free. You can access the source code and modify it and use it as a para-virtualized guest operating system. We only know, okay, personally, we only know Linux, which is widely used, okay? But when it comes to also other key important operating systems that people are using today, like Windows is not open source, and Macintosh is also not open source. You cannot get Macintosh and you go and modify the source code for you to use it. Actually, if they find out, that will be a court case. So already, this is the disadvantage of para-virtualization. So for them, they assume that if the guest operating system can be modified to make it aware that, you know what, you are virtualized, and the virtual machine operating system uses the hypercall to replace the sensitive 19 instructions in the virtualization. So the hypervisor program instructions are directly executed at the CPU non-privileged level. But already there's a disadvantage there, is because now only non-open source systems such as Windows do not support para-virtualization, because you cannot even access their source code for you to go ahead and do your things. And even sometimes the modified guest operating system, they have poor portability. You cannot move them because they have modified them and maybe tricked for them to work inside KVM, and now you want to use them inside Hyper-V. So sometimes, or maybe even transfer them and use them on another machine using KVM. So sometimes the portability was not that good. Okay, so now they're having those issues, and there Intel was wondering, so what is the problem, you guys? There are the 19 sensitive cases that are giving you hard time to use our CPUs in virtualization. Okay, you know what? We shall take care of that. We are going to come up with a technology in our BIOS settings, and we manufacture hardware or CPUs that actually already support virtualization technology. Okay, so Intel decided to come up with its Intel virtualization technology. Also, AMD decided to come up with AMD virtualization technology. Okay, so we have our Intel virtualization technology, and also we have AMD virtualization technology, and they make a CPU which already supports what we are calling virtualization, and that also leads us to what we are terming hardware assisted virtualization. Okay, hardware assisted virtualization. So with hardware assisted virtualization, right from the manufacturer makes for us CPUs which support virtualization, and all you just need to do is to install your hypervisor, and then the CPU will handle those 19 cases, because already that technology is embedded in the CPU, and if you go ahead and you enable it, you will be able to know that, or you'll be able to use your hypervisor or virtual machine monitor without having issues. So we saw in full virtualization and para-virtualization, the physical hardware did not support virtualization, and by default. So Intel and AMD and IMB and other key players said, but if the CPU support virtualization and are able to identify the 19 sensitive instructions, this would be a revolutionary change to CPU virtualization. So that's why today most of the commodity x86 CPUs support hardware virtualization technologies, like I've already mentioned, Intel's virtualization technology VTX and AMD's virtualization CPU. So when you put all those together, all other manufacturers makings together, we have these privileged instructions with a new CPU executing mode feature that allows hypervisors to run a new root mode below ring 0. So there's some kind of root mode below here. There's some kind of root mode below our ring 0, okay? And whenever the hypervisor is running, it is running inside. You can imagine that this is our hypervisor, this is root 0, and we have some kind of, we have our hypervisors running just within that root mode, okay? And this is what we are calling hardware assisted virtualization. So what they do, they produce CPUs that support or take care of the 19 sensitive cases. For you to be able to know if your computer supports, let me share my entire screen. For you to be able to know that your computer supports virtualization, you can actually just go to your task manager, or even in your BIOS, and you go to advanced settings, and then you're able to check and see if your computer can support virtualization. So when we check here under our CPU, we see that actually my virtualization here, we see that my virtualization is enabled. When we check here, we see that my virtualization is enabled. Okay, here, right here, let me just circle that my virtualization is enabled and my CPU supports, and this is what we are calling hardware. So the CPU is manufactured with the ability to handle the 19 sensitive cases which were giving us a hard time in full virtualization and para-virtualization. Okay, so let us move now to the next module, which we are calling memory virtualization.
Excuse me, Mr. Ssendi.
Yes, please.
Question.
So in case you wanted to enable virtualization on your machine, how would you do it?
The best way you do it, you go into your BIOS settings, depending on the kind of make that you have, either HP or Dell. You press either F2, F10, F8, depending on your make of your computer. Go to your BIOS settings. Then in the BIOS settings, always look out for advanced. Then you go into advanced, sometimes even boot. You can find it under boot. Then look for virtualization technology and enable it. Then you're good to go. Sometimes they are enabled by default, but sometimes if they are not, and you check and it is not there, you just go ahead and you enable your virtualization there.
Thank you.
You're welcome.
I have a question.
Yes, please.
My question is in regard to the CPU. I've had so many concepts that I've not heard about before, like 19 sensitive cases. So I think there was no background on CPU, really.
There was no what?
We can get a little bit of foundation knowledge on the CPU and how it acts, and then the bit of when you're trying to virtualize. It's when we virtualize a machine, like when you set up a VM, there is something you're trying to achieve, like you're trying to maximize the resources, you know, to.
All right. Thank you for asking. A CPU, I didn't get into the background because there's not so much background, and this course is not meant to dive so much into the CPU, but for you to understand, the CPU is what we are calling a central processing unit. Do we agree? It's a central processing unit, or some people call it the brain of the computer. And what the CPU does, basically, it executes all the instructions that make up a computer program. We all know that a computer program is a set of instructions put together to achieve a given task, isn't it? So the role of the CPU is to execute that. This program is telling me ABCD. Let me run that, execute it, and maybe the user is still using it. Let me go and store it somewhere in my address memory, and I'll call upon it when I need it. Okay, so basically, think about the CPU as the brain of the computer. Like what thinks for the computer that you should do this, you should do ABCD. So it is just a processor, or sometimes people call it the main processor of the computer, but its role basically, it is to process all the instructions that are sent to it for execution. Okay, so when we are talking about the ring, because now we want to focus so much on virtualization, and yes, it is true, like you said, we want to utilize these resources. What will happen, we have our CPUs, let's say we have 2 of them, or we say we have 4 cores, but all of these, we are not utilizing all of them. Maybe it's a processor and we have like 16 CPUs available, but we're not utilizing all of them. And yet we can virtualize and have other machines running and using the same processors, but they believe that actually they're using different processors with their own different hardwares. But it was important for us, before we actually even get to know about the different types of full virtualization, para-virtualization, to know about these rings. That's why I hinted or talked about them. That basically, as the CPU is going to execute these instructions, we should take note of this, that for you to be able to change the state of the hardware, we need either to have privileged instructions, and we have 3 domains. We have domain ring 0, 1, 2, and 3. And the people who designed the CPU architecture designed it at the back of their mind for protection purposes. Okay? So to give more security to our hardwares, imagine if you made a program and it can directly access your CPU and maybe force your hard disk to format without necessarily having to call the operating system to do that on its behalf. So basically, think of these as just privilege levels, just like you would be creating accounts on your computer and say this is an administrator, this one is not administrator, and there are just 4 of them. And we are saying that the application runs at ring 3, which is the least privilege, and also the operating system runs at ring 0, which is the highest privileged. Okay, so basically, usually I just go through these slides because we just want to point you to the direction of virtualization. And whoever designed the content of the course, they knew very well that they are not designing a computer science course, but rather we are focusing on cloud computing. But it is important that we hint and talk about these things. So that when I'm talking about 19 sensitive cases, you already know that we have common cases and common instructions, and privileged instructions. So you already know what I'm referring to. I'm not just telling you about the 19 and you're wondering now 19, what are even instructions and why don't we just go ahead and manipulate and use those instructions? Or why doesn't CPU just go ahead and picks up whatever instruction it receives and it executes it on behalf of the application? Thank you. All right, so let us look at memory virtualization. So just like the way we had to virtualize, basically to use, now if you go ahead and you look at my CPU, for example, just to see, I hope I'm not over using it, task manager, performance. This is not a server, but I'm just using about 37%. And you could find a server if you're just running an operating system just like this, you are utilizing about 5%. And let's say you have maybe another application, you need another machine for your database. It would be unwise for you to go ahead and invest into another expensive machine when you have resources which are underutilized, and yet you could actually emulate them and utilize them, and you continue and you have two virtual machines running on the same machine, and the end goal of you having the two database servers running at the same time is achieved with actually better functionalities of you being able to know that you could actually migrate it, hot swap it, and get rid of some fault tolerance. So we are able to virtualize, but you wouldn't be able to do that. There's no way you can virtualize, there's no way you can install two operating systems on the same hardware resources at the same time and they run simultaneously. You will need virtualization to do that. And after virtualization, you're able to create different machines on that very machines, and they use the same resources, utilizing them, and while you achieve efficiency. So let us look at memory virtualization. Memory virtualization, this is also an important type of compute virtualization besides CPU virtualization. Like we said, memory, we all know what we use memory for. And in this case, we're looking at, are we looking at volatile memory or non-volatile memory? Can we get a volunteer to answer that?
Volatile memory.
We're looking at volatile memory. And this basically will help us to store our instructions or programs that are in use as long as we have power. And when power goes off, then we lose all that memory. But it is important because remember now you don't store anything or the instructions that are being executed in the CPU, but rather you store them in the memory, okay? So this, it helps us to actually store the working data or the things that we are working on, all our instructions, all our machine code temporarily. Imagine if whenever you opened your browser or your document and you jump into another program which is being executed by the computer, then the other one closes automatically because it's not stored anywhere in your memory, or it is not cached anywhere in your memory. So that's why we need to look at memory. But also memory, the way memory is allocated, we have our physical memory in our computer, and usually there are some slots available, like 2 or 3, depending on the make or even the server, 2 or 3 slots in our computer. Okay. How many CPUs can I assign to the virtual machine? That entirely depends on how many CPUs you have available, that are available to you. But when we are looking at quality of service, we shall be able to see the quota. What are you actually supposed to allocate when you have what? So we shall be looking at that. But that entirely depends on how many cores you have available to you on your physical host or in the cluster. But you can assign as many as you want if you have them available. Okay, so I was saying we have our RAM, physical RAM, okay, our memory, which we put in our computer. And our physical RAM here, what the CPU does, it uses the memory addresses that are created to map the data that is, or the code or the working data that is going to be stored. And usually it does address it in a way that follows sequentially. So we have 0, memory address 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on, 13, 14, 15, 16, and 17. What usually happens is that as you are working on things, it will get a memory address and it says, you know what, this instruction or this code, I've stored them temporarily in memory address 5, okay? And as it is cross-checking with its mapping table and the user does anything or calls anything that was stored in memory 5, the CPU will call upon the things it stored in memory 5 into and it starts processing them from its mapping table, okay? So it will call upon things in this memory address and then it will start processing them. So the challenge now comes, how will the CPU, okay, I was seeing the messages in the chat. All right, how will the virtual machines now, because already the host operating system or the host CPU does the memory allocation and we already have our mapping table. So how will our virtual machine here be able to allocate the memory and which memories actually they are going to be able to share with other CPUs, okay? So with CPU virtualization, virtual machines running on top of a hypervisor layer have replaced physical hosts to run the application. So multiple virtual machines can run on the same host that we have already agreed and we have already seen. And the host usually has one or more memory modules. So how can memory resources be allocated to virtual machines properly? Okay, so memory virtualization was introduced to address this issue so that these virtual machines can actually allocate themselves the same memory from this address that is already existing within our host memory. Okay, so but you should take note that the memory address always of the physical address usually starts with physical address 0, like I showed you here, 0, 1, 2, 3, 4. You'll forgive my handwriting, I forgot my writing pad. 6, 7, 8, 9, 10, and 11, 12, and 13, and 14, and 15, and so on and so forth. So the memory address of the memory address starts from the physical address 0 here where we're seeing, and then it goes on continuously. So, and what you should also take note of is that memory address space is allocated continuously. So now this challenge comes in. So after virtualization, the problem occurs that there's only one memory address space whose physical address is 0 and it is already taken up. So, and this virtual machine cannot go ahead and now start using the address of the physical memory, and it says also I'm addressing as 1, 2, 3, 4 like that continuously. Okay, so it is impossible to ensure that memory address space of all virtual machines on the host start from the physical address is 0, because now 0 will already be taken by this one, and if it starts with 0, this memory address of the physical address will be taken already if this guy uses memory address 0. Okay, so memory virtualization now, it is a process of centrally managing a physical memory of a physical machine and aggregating the physical memory into a virtualized pool of virtual machines. So memory virtualization creates a new layer of addresses that is the address spaces of virtual machines. and they are made to believe that they are running in real physical address space, when in fact their access requests are relied on by the hypervisor. Okay, so the hypervisor stores the mapping between the guest machine address spaces and the physical machine addresses, like you see here. Now, for example, let us try and come up with a mapping table of virtual machine 1. Okay, physical address mapping table. We have our virtual machine 1. So we have already seen here. Okay, so what will this correspond to in our physical or our host memory? It will correspond to 1. Just look at the patterns, the way they are shaded. They're just shaded to show you where these different virtual machines actually. This was think about this as virtual machine 2, 3, and 4. Okay, so where does this virtual machine, which memory we see it is 0? Okay, so we have our 0 there. What would be the next one? We look through the pattern, it will be 5, isn't it? What will be the next one? It will be 6. Are we together, class?
Yes, we are.
Yes. So the next one would be?
To be the number which is below
17.
Yes.
7, which
It will be 13. And so on,
Yes.
and so forth. Even this guy here, what will be the first virtual machine address, memory address in the physical address? It will be 2.
2.
And the next one?
4.
4.
And the next one?
2.
10.
10.
Okay.
10.
Yes, and so on and so forth. So
14.
So that is how our virtual machines and the hypervisor are able to utilize virtual machine virtualization. Thank you so much. Thank you so much. So let us also look at input and output virtualization. So with input and stroke output virtualization, emulation, or what we are calling full virtualization. We have already looked at full virtualization, and we know that the hypervisor traps and emulates all the instructions that are sent to it. So here, there's a complete simulation of hardware, for example, keyboard and mouse, all these input and output devices, they are fully emulated, and our virtual machine thinks like it is actually directly accessing these hardware resources, but yet in actual sense, it is the hypervisor accessing them on its behalf. So access to such hardware depends on the capture focus by the host and leads to poor performance in some cases. Okay, so for example, we are using here full virtualization. When I open my my VMware workstation, and I want to switch in between my virtual machines. Okay, and I want to switch in between my virtual machines. Just a moment. Okay, so if I power it on and I want to switch the keyboard and my mouse, when I click inside, you see my mouse has disappeared, isn't it? Even when I pass now some Windows commands, like Windows key, it will not load my start menu, simply because now my virtual machine has taken over my input and output resources. But now, what happens is, if I want to release them, I need to press some key, which is Control-Alt, and now I have released them for my host machines, for my host machine to use. So that's why we are saying here, that access to such hardware depends on the capture of focus. So if the capture of focus is on your virtual machine, then usually those key resources will be available to that virtual machine. And sometimes it leads to poor performance in some cases. So let us also look at para-virtualization. So in this case, access to hardware drivers is transferred from input to output front end to the back input and output back end. This mode is usually only used for hard disks and network interface cards and delivers high performance. So we are saying para-virtualization when it comes to input and output virtualization. Usually the access to hardware drivers is transferred from the input and output front end drivers to the input and output back end drivers, and this mode is usually used for hard disks and network interface cards, and it delivers high performance. So we also have input through, where we are saying hardware devices capable of input and output through, such as hard disks and NICs. Hard disks usually and NICs, they have input and output through. Because why? Pass through. Because now I don't have to when my virtual machine is using my hard disk, if it has a partition there or anything, I can still continue to access my partition and I am able to do my work. If my virtual machine is accessing my network interface card, my host machine still accesses the Wi-Fi and I am able to conduct my class and able to interact with my students, and we have a successful session. So usually they are directly allocated to the virtual machines they're creating it. So in them, they say usually DOM0 allocates hardware devices but does not take part in the access of the hardware. DOM0, we shall look at it later. So there is the requirement of hardware support in case you're using DOM0 to access, or in case sometimes you're using throughput. Sometimes you may be required to install some kind of drivers or hardware support. Okay, so now let us try to look at what we are calling the cloud computing and virtualization. Okay, so we already looked at virtualization and we said we have our physical machine here, which we can emulate and virtualize, and we can create multiple virtual machines or resources from it, isn't it? All right, so which you can create multiple virtual machines. And it is the same concept still in the cloud. We have the cloud is building on this kind of analogy to actually have these resources available to you from the cloud. So virtualization is a foundation for cloud computing. Take note of that. Okay? But virtualization can happen or can exist without cloud computing. But cloud computing can never exist without virtualization. Please take note of that. All right. So let us also try and look at the mainstream compute virtualization.
I beg your pardon on that.
I'm saying that virtualization is a foundation for cloud computing. Okay? And virtualization can happen without cloud computing. You saw me as virtualizing my virtual machines on my machine, virtualizing my resources, and I was creating them. That was not necessarily cloud computing. But for cloud computing to happen, there must be some kind of virtualization somewhere. Okay, so you cannot have cloud computing without virtualization somewhere. All right.
All right, thank you.
You're welcome. So CPU virtualization, memory virtualization, input and output virtualization, which you have looked at, they are all implemented to enable the reuse of physical resources so that you can be able to reuse your CPU, can be able to use your RAM, can be able to use your input and output devices. So multiple virtual servers can run on one physical host at the same time, and each virtual server can run different workloads. This one improves hardware utilization And also everything about a virtual server can be packaged into one single file or a folder. And what characteristic is that of virtualization? What feature is that?
Encapsulation.
Perfect. It is encapsulation. You guys are in class. So we are saying they can all be packaged into one single file or folder. So this breaks a tight coupling between software and hardware and allows virtual machines to migrate across hosts and even data centers. And this now improves reliability of our workloads, and also we can migrate our virtual machines, so it also creates about fault tolerance. So in cloud computing, mainly we use virtualization to implement infrastructure as a service, cloud services. Because when you're virtualizing, actually, you are just providing hardware equipment, isn't it? All right. So we already mentioned before, we have three types of cloud service models. I've already mentioned one, and I said it is infrastructure as a service, which we achieve after virtualization. What else do we have?
Platform as a service.
Platform as a service, yes. What else?
Infrastructure as a service.
Software as a service.
And what?
Software as a service.
Yes, awesome. Software as a service. So some platform. All right, thank you. So some platform as a service and software as a service are implemented based on virtualization, okay? And some are even implemented based on physical hardware and distributed computing.
As a service.
Yes. All right. So we earlier on also said, for the people who have joined us, that cloud computing is basically a business model that provides users with IT services which are available anytime and anywhere. Do we agree? And virtualization is an important technical means for cloud computing implementation that we build on virtualization for us to be able to provision those services so that the users could actually share those CPU resources at any time and anywhere. Okay, and basically there are many mainstream virtualization technologies, but we are going to focus on these two. We are going to focus on open source and closed source mainstream virtualization technologies. When you hear of the word open source, Tim, tell me, what comes to your mind? What do you know? I've been mentioning it, hinting on it. What do you know?
It's free to use and source code is available.
Source code is available, yes. It is free to use.
You
and
can get the source code and modify.
Yes. And we are seeing that under this mainframe, we have KVM and we also have Zen. And KVM runs under Linux, okay? And Zen is a type 1 hypervisor we already saw, which is installed directly on our hardware resources. KVM is installed on top of Linux, which makes it type what? Tim, which makes it type what?
Type 1.
Type 2. Perfect. Excuse me, just a moment.
Then is type 2. Type 1. Then is type 1.
Sorry about that. So we said this is type 2. As long as it is hosted and it is running on top of an operating system, it becomes type what? Type 2. And please capture this slide in your mind because it will help you a lot. Now, this is the time I ask you to cram.
Are you sure?
Okay. So, but
Why cram? Why cram?
I'm just being sarcastic. So we have open source. Well, we said it is free and we can access a source code. And we are seeing we have Zen and we also have, we have KVM and we have Zen. And we're now having a closed source. And closed source, I'm not going to ask you to tell me that the definition, it is the opposite of open source. This, you can't access the source code and you have to pay to use, isn't it? And here we are having Hyper-V by Microsoft. And you can see we are having VMware EXI by VMware. And also we're having Huawei FusionSphere by Huawei. Okay? And these are all powerful virtualization solutions, all technologies. And as you can see, Hyper-V is type 2 because it is installed in Windows. VMware is type 1, okay, because it is installed directly on the server, directly on bare metal. And sometimes this could also be, it depends, it could also be, depending on how you have installed it, but you could install it alongside or on top of, when you just installing Fusion Compute, you can install it on top of KVM in Linux, which makes it type 2.
So,
But the solution you buy out of packet is type 1.
Hyper is 2.
Okay, as muting someone. So, but the solution you get out of box is type 1 solution, okay? All right. So, basically, those are the main stream technologies for virtualization, okay? Right. So, let us look at Zen versus KVM. I've already said on the previous slide, what type is Zen and what type is KVM before we talk about anything?
KVM is type 2.
Okay.
Zen is type 1.
Zen is type 1. Awesome.
Zen is
you guys are going to
type
discipline.
1.
You guys are going to discipline this exam. Okay. So when it comes to Zen, you can see that it's already type 1. It is installed directly on top of our bare metal. But what happens, it has one privileged virtual machine or backend or virtual machine, which we are calling DOM 0. And for it, this one is what is having all the privileges to access the hypervisor or to call the hypervisor to access the hardware resources. So the other virtual machines which are created on top of Zen, which are now the DOM user, here the DOM U, they actually now use the front end to call the back end of DOM 0, which now calls the hardware drivers through the Zen hypervisor. Now that is Zen, okay? And when it comes to KVM, like already we said, it runs inside the Linux. It's a kernel inside the Linux operating system. So on top of our hardware, we install Linux operating system. And then inside our Linux operating system, we install KVM. And now KVM also works hand in hand with QEMU. And QEMU emulates the input and output operations. And then we have our virtualization environment where we can, these are actually our virtual machines, and we can have our other applications on top or inside our Linux. So we're going to look at KVM in detail, okay? So, introduction to KVM. So what is KVM? We have already said, you have already told me that KVM is type 2. full virtualization solution, and it is a Linux kernel model. Okay, because you have already seen it is installed inside the Linux kernel, isn't it? So a physical machine with a Linux kernel module installed can function as a hypervisor. Are we together? So which does not affect other applications. These are the applications that can be running alongside or inside the Linux operating system. So virtual machine is one or just a process inside our Linux. So it is handled or seen as a process. So you can either run it or kill it with a command. You can run a command to kill that process because it's just a process inside our other processes inside our Linux operating system. So after the KVM module, this module here, after it is installed and enabled in our Linux, we have now 3 running modes that are added. We have the mode which is called the guest mode. Okay. We have a mode which is called the guest mode. We have another mode which we are calling the user mode. Okay. And finally, we're having the kernel mode. And we are saying that when it comes to the guest mode, virtual machines, including their CPUs, memory, and let's say disks, or what we could call, yes, this just said disks, and disks, they usually run in a restricted CPU mode. They usually run in a restricted CPU mode. Next week, I'm going to get my writing pad. I forgot it somewhere so that I am able to, I'm used to writing, but my handwriting here is defeating the purpose. So we also have the user mode, which user mode now, we are saying the quick emulator now, which we are calling the QEMU here, quick emulator, typically runs inside the user mode. And QEMU, I want you to take note, QEMU emulates our input and output requests. Take note, QEMU emulates our input and output requests. So then finally, in our kernel mode, which I talked about, hardware now can be operated. So when the guest operating system executes an operation, an input and output operation, or a privileged instruction, let's say, the request is sent now to the kernel mode again to operate the hardware. So KVM consists of those other 3 parts that we are now going to talk about: the kernel, KVM kernel module, QEMU, and pay attention to QEMU, this KVM kernel module, QEMU, and the management tools. And we're going to look at the management tools later on, okay? And the management tools. So the KVM kernel module and QEMU are the core components of KVM. Please take note. We are saying that the kernel module, the KVM kernel module, and the QEMU, they are the core components of KVM. Okay? So kindly take note of that. And there's a reason why I am telling you to take note of that. So the KVM module, this guy here, the KVM module is the core of KVM virtual machine, and this module initiates the CPU hardware and enables the virtualization modes. So the running guest machines in this mode and supports the running of a virtual client. So KVM is composed of 2 kernel modules, the common module and the processor specific module. I won't get into the details of those ones. You can go ahead and read later on, because I know they're not going to be relevant for this part, but I want to emphasize that the VM requires other input and output devices such as NICs and hardware disks besides CPU and memory. Therefore, we shall need Kemu. I said Kemu does what? Class?
Emulate the input
Emulates our
Emulates
Yes.
requests.
Yes. Therefore, Kemu is required to implement other virtualization functions such as input and output operations. And this we conclude by saying that KVM kernel module and Kemu, they form a complete virtualization technology. I repeat, KVM kernel module and Kemu, they form a complete virtualization technology. Kindly take note of that. Okay? Have we? So, in addition to virtualization of different devices, Kemu KVM provides native tools for creating, modifying, and deleting virtual machines. Then also there's something important that we are going to be talking about, or that we're going to be introducing here, which we are calling Libvirt. Okay, so Libvirt is the most widely used tool and API for managing KVM virtual machines. KVM, I forgot to mention, it is a kernel module. I think I mentioned that, didn't I? I did, didn't I? All right. So we use Libvirt here is the most widely used tool and API for managing. What is the time? I shouldn't forget our break. Okay, for managing the KVM, for managing KVM virtual machines. We are saying that Libvirt is an open source project. Take note, open source project, and it is a powerful management tool. Please take note, powerful management tool. I emphasize management what? Powerful management tool. And it is able to manage virtualization platforms such as KVM, Zen, VMware, Hyper-V. Libvirt is an API developed using the C language. However, other languages such as Java, Python, Ruby on Rails, Perl, etc. can call Libvirt API to manage virtualization platforms. So Libvirt is used by many applications, and in addition to Vish command set, these guys that you're seeing here, the Vish command set, Vit manager, Vit viewer, Vit install, and others, okay, they can manage KVMs through Libvirt, sorry. Okay, so in cloud computing, there are various hypervisor, and each hypervisor has its own management tools, and parameters are complex and difficult to use. Like I'm saying, hypervisors are not unified, and there's no unified programming interface to manage them, which severely affects cloud computing environments. So with Libvirt, remember it's an API which can be called, and we have seen it manages quite a number of them. Okay, it can connect to various hypervisors such as we have already mentioned KVM, we have mentioned Zen, and provide APIs in various languages. So Libvirt serves as the middle layer between the management tool and the hypervisor, and is completely transparent of the upper layer users. So Kemu is an emulation software tool for implementing input and output virtualization. It has poor emulation performance. For example, if Kemu is to stimulate a NIC of a Windows virtual machine, the NIC interface rate displayed on the system is only 10 Mbps if we use Kemu. Okay? Actually 10 MB per second. Okay? So it cannot meet the high NIC rate requirements for some applications. That's why they came up with a new technology, what they are calling VirtIO or virtual, depending on how you want to pronounce it. That's why they came up with that technology in Windows virtualization. VirtIO can increase the net, can, and I repeat, can. It's not a must, but can increase the rate of the Windows virtual machine network interface card from 10 Mbps to 10 gigabits per second. Okay, so let us also try and see how QEMU or Libvirt is able. Let us look at Libvirt here briefly. So we are seeing we have our virtual machines, we have our hypervisor, we have Linux host, and then we have our physical host. So we can have our API here, our management tool of Libvirt, which can help us to manage, our virtual machines here. Okay, virtual machines and different hypervisors, and we have Linux. So when you install Libvirt, it can help you manage different hypervisors and also manage different virtual machines or and change their states or status. So let us look at this before we go for a break. Let us look at that before we go for a break. And we are looking at the KVM input stroke output process by default. Okay, so by default, we have our guest operating system here. Our guest operating system needs to access our physical hardware here. Okay, so what happens when a user sends in a request or an instruction, it goes to the device driver, which device driver now is going to use the input and output trap code within the KVM module, which will now go to the shared page. That is stage 3. It goes to the input and output shared page, and then after QEMU emulation code will be sent to the QEMU emulation code. And the QEMU emulation code now will be sent to the device driver, and then the device driver calls the hardware. And then also, of course, at the same time as this guy receives this, he will send a notification to the QEMU emulation code that, you know what, I've sent some things in the shared page, please kindly receive them. Then also this one will send back the results back to the input trap code, back to the device driver, and back to the guest OS. I suggest that we first go for a break now, and we are going to resume from here for the remaining part of the class. Thank you so much.
Are we getting the roll call list right now?
Oh, yes, I'm going to share it now. You fill it in during the break. We're having a break and we're resuming at exactly, we're resuming at 6:50. We're resuming at 6:50. And I strongly advise that you please don't miss the next part.
Okay.
All right. I strongly advise that you don't miss the next part. So I'm going to share the.
I'm going to share attendance.
I'm going to share the attendance link. You should have received it by now. Oh. You should have received it by now. All right.
Yeah.
So by 6:50, we resume with the second part. And we shall also do an introduction to network basics in cloud computing. And then we shall call it a day at exactly 8 p.m.
Hi, some guys have disappeared.
Hello, are we back? Are we back? Are we back? Are we back?
Yes.
All right, that is good. I forgot to pause the recording. So, let me see. I'm seeing 47 people on the call. I assume they will join in more later, or I'll be forced to make another tendency. Okay. Friday, I'm seeing your hand is up.
Yes, sir.
Yes, yes, Friday.
Yeah, I just want you to pardon for me. There is a part you were talking about on issue of virtualization solutions. And you talked about type 1 whereby this solution is do do not need to run on hosted OS. So basically, I just wanted you to pardon for me those examples of those solutions in both type 1 and type 2.
In both type
Thank
1
you.
and type 2. Let me take you back to this slide. Okay.
Okay.
Yes, we said type 1, it is like an operating system itself. Okay. You install it directly on top of the hardware resources. You remember? And then we said type 2, you install the hypervisor alongside or on top of an operating system. Okay.
Yes.
And we have Zen here. We have, these are some of the hypervisors available. Okay. These are some of the hypervisors available. Let me get my automation. And we're looking at Zen, we're looking at KVM now. We have already seen KVM. Where do we install KVM?
KVM, you said runs on type 1. It doesn't need no type 2.
Yes.
Type 2, it runs on Linux, right?
Yes. So already that makes it type 2, isn't it?
Yes. Yes.
It makes it type 2 because this is the kernel module that is installed and enabled in Linux. Okay. And we said Zen, for it, it is more like an operating system itself. It is installed directly on top of the hardware resources. You have your physical machine, you install Zen, and you start virtualizing those resources available to you. Okay. And usually it is mainly used when it comes to Zen servers. They're very common, and people who have data centers. And then also, this is open source. Okay.
Yes.
Someone is automating my screen. Please do not automate on the screen. Thank you. And then we also have another open source, which is for free, though sometimes it can be paid for. We have Oracle VirtualBox, isn't it? And Oracle VirtualBox, you can, there's a tool, there's one you can install in Windows. There's one which you can install in, actually, I don't think Oracle is open source. I think Oracle is closed here. Oracle VirtualBox. Okay, because you don't get access. I'm yet to find out, but most likely I think it is open sourced. Okay, so we have them. Then we have Hyper-V. Hyper-V is by Microsoft. Okay, Microsoft, and it is installed along all with Microsoft Windows. So it makes it type what?
It makes it type 2.
Type 2. Awesome. And we have VMware EXI by VMware Workstation, and it does not need to be installed on top of any operating system. It is installed directly on top of hardware resources. It makes it type what?
1.
Type 1.
Type 1. And then we also have Huawei Fusion Compute, which is also like EXI for VMware Workstation by Huawei, and it is also installed directly on top of hardware resources, which makes it type
1.
Have I answered you?
Yes, thank you so much.
You're most welcome. So let us proceed with our slide here. Okay, we're looking at how the input process happens in KVM. So we are saying here that a disk or an operating system, let me put it in full screen mode, sorry. So we are saying here that an operating system or a disk of a virtual machine, I'm hearing my echoes. Could someone please mute the microphone? So we have, let me, okay, mute you because I can hear myself. All right. So we have our disk here. Like, let's say which wants to make an input or output request. Okay. So the disk sends the request input, output, a trap code or the capture program in KVI module, this trap code to capture the input output operation request, which also performs corresponding processing, then puts the processed request into the input and output shared page here at 3. After putting it in the shared page, KVM module, this module here, notifies KEMO input output emulation code that, you know what, please obtain the information about the input and output or output request that I have put in the shared mode. So after receiving the notification in KEMO, so then after receiving the notification, KEMO obtains the details from the shared page or the information about the input request. And after KEMO stimulates the request and calls the device driver running in kernel-based mode to actually go ahead and perform the request on the physical hardware resources. Okay, so the input output operation is then performed on the physical hardware resources through the device driver. So therefore, KEMO after that returns the result to the shared page and notifies KVM that, you know what, KVM, I have something for you. So that the operation or the input and output operation is complete. Then this trap code, the input and output trap code, then returns the result from the shared page to the device driver, and then the operation now is returned to the guest operating system. So there are about like 8 steps during the default process without introducing VAT-IO. Okay, so when we go ahead to the next slide and we introduce VAT-IO, when we go ahead to the next slide and we introduce VAT-IO, this one, let me clear my drawings, and we introduce VAT-IO, we said that VAT-IO, now if the input, what you said already about VAT-IO, that if it is introduced on a Windows machine, it can support up to 10, or that our NIC network interface card can support up to 10 gigabits per second. We said that also, kindly remember that. Okay, so here, the virtual machine initiates a request or an input and output operation request. Then the input and output request is not captured by the input and output trap code. This guy, remember the trap code, the program which used to capture the codes then. This time round, the input or request is not captured by that, okay, by that emulation. I'm hearing some feedback. Ogwang, let me mute you all. Is that okay?
Samuel?
Yes, please.
First go back. Sorry to take you behind a bit. First go back on the other diagram. No?
Which one?
That one.
When
an input is put, as it reaches the IO trap code. Yeah, you say that the KVM module sends a notification to the emulation code.
Yes.
That when that input reaches that trap code, and then before that trap code sends it to the IO shared page, does it mean that KVM, as it receives that instruction first, it informs the emulation code before even IO trap code sends it to the shared page.
No. The trap code receives, traps actually the request from here, from the device. After trapping, it processes. And after processing, making the processing, it sends or puts it to the shared page. At the same time as it is taking it, all it is when after putting it there, this one now notifies Kemo that Kemo, I have something for you. Please go, your delivery is ready. Please go and pick it.
Okay,
yes.
So it works simultaneously.
Yes. As it is sending to the shared page, also it notifies Kemo that I have I've put something in the shared page. Kindly pick it from there.
Okay.
Yes.
Thank you.
You're welcome. So here you see already that the steps have somehow reduced. And we are saying that this time round, our trap code does not capture the input and output request. Instead, the request is stored in the V-ring buffer. Okay, it is stored in the V-ring buffer. So between the front end, this front end here, and the back end driver, we have the V-ring buffer. So this time around, the trap code is not trapping the input and output request. Instead, it is sent or stored in the V-ring buffer. So what Kemo does now, it obtains that information from the V-ring buffer, and then the back-end driver here, after Kemo obtaining the information, it directly calls the actual physical driver to perform the input and output request on our physical hardware. Okay, so the operation is completed by the device driver. After the request is completed now, the back-end driver or Kemo will get that, and it returns the result to the ring buffer, which ring buffer and then KVM will also again notify. Okay, what happens here when this guy puts here, KVM still notifies. Also, what happens here when this guy puts there, KVM also notifies the front end driver that, you know what, the operation, there's something for you in the back end driver. Then the front end driver will obtain the result from the ring buffer. Then the front end driver returns the result to the application that initiated the operation. So the advantage with this, you can already see that the process has been minimized. The advantage with this is that it saves hardware resources for Kemo emulation, since we don't have the trap code trapping the request, translating it and processing it, then putting it in a shared page, and then after the Kemo picking it from there. And also, everything now is done between the front end and back end driver, and also it reduces the number of request paths that are involved, and therefore improving the performance of virtualization devices. So, however, virtual has some disadvantages, and for some old and uncommon devices, they cannot use VirtIO, but can only use Kemo. Those devices that are old, they can only use Kemo, they cannot use VirtIO. Okay, they only use Kemo. So let us also look at Fusion Compute. This one is a chap topic. Let me first check what is in the chat. George, I'm not understanding the question in the chat. Can you receive all the explanations of all terminologies used? Please let us focus on what we are focusing on in this course, but you can always go ahead and read more. because you cannot finish all the terminologies that are available in cloud computing. Wait a minute and try. What that happened to me yesterday? Why am I failing to submit my attendance? It is probably because of your network, or if you're using VPN and you have to click on either traffic lights or cross paths or something like that. But basically, that is it. So is virtual addition software installed on top of hypervisor. Virtual is part of the management tools that are brought about by Libvirt, and we have just looked at it. Okay. All right. So let us look at Fusion Compute. So FusionSphere here, Fusion Compute is part of FusionSphere, and FusionSphere Virtualization Suite is a leading virtualization solution. It is a solution significantly which improves the data center infrastructure efficiency and provides the following benefits for customers. I should mention that also the government of Uganda from this year coming forward is going to be using FusionSphere as its #1 virtualization technology. It hired Huawei to be its ICT consultancy company. So that means that also people who have certificates in Huawei technologies also stand a chance, maybe, if maybe there's a role that is made available, and they need someone to take on those roles. But saying that, why? Because it improves infrastructure resources utilization, data centers, significantly accelerates service rollout, reduces power consumption in data centers because of the distributed power management, provides rapid automatic fault tolerance for which also is achieved through live migration, and of course quality of service policies that can be configured in case of high availability. So FusionSphere Virtualization Suite basically virtualizes hardware resources using virtualization software deployed on a physical server. And the software that Huawei uses to virtualize is Fusion Compute. We are saying that Fusion Compute is a cloud operating system software that is part of the FusionSphere Virtualization Suite, and it is mandatory. It's a mandatory component if you want to use FusionSphere to virtualize the equipment. So what it does also, like any other virtualization solution, it virtualizes hardware resources and centrally manages virtual resources, service resources, and other user resources. Okay, so Fusion Compute basically consists of two things: the CNA, the computing node agent, CNA, and virtual resource manager, the VRM. Okay, we're going to look at them shortly, and the VRM. So in addition to CNA and VRM, there's also the UVP, the Unified Virtualization Platform, which is a unified virtualization platform deployed by Huawei. So the UVP is a hypervisor like KVM and like Zen. Fusion Compute Hypervisor adopts the bare metal architecture and can run directly on servers to virtualize hardware resources. So with bare metal architecture, Fusion Compute delivers virtual machine with almost server level performance, reliability, and scalability. Okay, so we are having the virtual resource manager, and we're going to be looking at what the virtual resource manager does. And we're also having our CNA, which CNA computing node agent are installed on our machines in our cluster. Here, these different machines, which are having different resources also connected to them, where we are using this characteristic, I don't know if you remember it, where we are going to get all the resources from these CNAs or nodes or physical servers, and we put them into a resource pool. Who remembers the characteristic or advantage? Are people on the call?
It shields the
The
specifications of
differences of resources.
resource pooling.
Resources, but also resource pooling, because you see all these are different resources. There are storage resources, memory resources here, and CPUs resources already pulled together from different hosts there. So what the VRM, the virtual resource manager, what it does, it gives us the ability to manage the block storage resources in a cluster. We have different clusters. This is our cluster, cluster 1, which has different physical computers here or physical servers here. So what VRM helps us to do, it helps us to manage that block resources, also to manage the network resources. We shall see that somewhere as we go to the network bit that we have actually network, we have some kind of virtual network equipment inside our virtualization architecture. So we shall also be able to look at that in the coming chapter. Okay, so it also helps us to manage the network resources such as IP address, network interface cards, allocate IP addresses to virtual machines, and so on and so forth. Manage the life cycle of virtual machines that we are going to create, dynamically scale resources in a cluster, implement centralized management of virtual resources, and use user data, and also provide elastic computing, storage, and IP address services. Then also it allows operations and maintenance personnel to remotely access Fusion Compute through a unified web UI to perform input operations and maintenance on the entire system, such as resource monitoring, resource management, and resource report query. Once again, I repeat, kindly take note of this phrase. What VRM helps us, it helps us or allows operations and maintenance personnel to remotely access Fusion Compute through a unified web user interface to perform operations and maintenance on the entire system, such as resource monitoring, resource management, and report query. The CNA is also similar. CNA for Huawei FusionSphere, what we are going to install on these different machines so that we virtualize them. We are saying they are similar to KEMU plus KVM, and we said KEMU plus KVM form a complete
virtualization machine.
Yes, they form a complete virtualization solution. So meaning CNA is also a complete virtualization solution. So CNA provides a virtualization function. It is also deployed in a cluster into a to virtualize compute, storage, and network resources in a cluster into a resource pool for users to use. So the computing node agent is also based on the Linux operating system. So CNA also provides functions like a virtual computing function, managing the virtual machines running on computing nodes, and also managing the compute resources, storage resources, and network resources. Okay, so the next slide will better help you understand some of the advantages which I've been talking about. Quickly provisioning virtual machines. You can create the virtual machines quickly, and you can use the virtual resource manager to manage them, create them, delete them, modify them, and do everything that you need to do. And of course, you can use it's also a unified management of virtual and physical resources. So you can manage your physical resources still while using via VRM, the virtual resource manager. So you can manage your physical resources, your virtual resources, physical resources still, and your physical resources here as illustrated in the slide. So also these are the advantages I've been talking about. I've mentioned most of them, you have seen them. And I also emphasize for you to take note that it provides a unified UI portal allowing operations and maintenance engineers to remotely access the Fusion Compute system to monitor and manage resources and create services. Okay, so don't be confused if they tell you it allows IT managers. It is specific to the role. You have to be an operation or maintenance engineer. Okay, so Of course, you have also talked about other functions. You can go ahead and read about them in the detailed material which I shared in the group, which is readily available to you. So now there are some questions before us here, team. Some questions before us here, and just kindly just try again if you have failed to register. It is important that you register. It's a Google form, so it could be purely your network. Just try again. Just make sure you try once. Let me see your name, and I cross-check with the form and see if it has been submitted. I have failed Zipporah. Let me try and look for Zipporah here. Let me try and look for Zipporah. Zipporah. Okay, let's see. Okay, I'm not seeing you, so there's a possibility that you haven't yet registered. So you can just try again and register. It should be able to work. So, members, there are some questions before us here, and we are seeing that in compute virtualization, which of the following allocates CPU and memory sources to virtual machines? Okay. We have A, the guest operating system. We have B, the virtual machine monitor. We have the hypervisor, and we have the host operating system. Okay, can I hear someone talk to me?
C.
Who is this?
It's Daniel.
You're saying C. Daniel is saying C. Daniel is saying C, yes. Who else?
My answer is B.
Your answer is B. Stuart?
Yes. No, Emmanuel. B.
Emmanuel, oh, sorry. I'm also seeing a Stuart in the chat, so he said B. Okay. Anyone else? Joan, what happened to you today? You're over quiet. Are we okay? I'm seeing Joel is saying B. Come on, team, let's try. Joan is saying, Joel is saying B. Other people are saying B. B here. Okay. I think people are saying B. Others are saying C. Okay. Friday, I see your hand is up.
I think the answer is C.
You think the answer is C? Okay. Also, Friday is saying the answer is C. Gracious Emma Olet said the answer is D. Olet said the answer is D. Evan said the answer is B. Okay, so I think if you are all in the paper, Berina said that the answer is C and C and C. I'm seeing Naiga is saying it's C. I'm seeing Rita, Anita, she's saying the answer is C. John is saying the answer is C. So, okay, Cynthia is saying the answer is C. This is what I would say. If you are all in the paper, you would actually all get the answer wrong.
Aye.
Eh? Why? Someone has said I. Okay. Why? Those who have said C, you are correct, but partially correct. And those who have said B, you are correct, but partially correct. Those who have said D are totally wrong, and no one has said A. So in computer virtualization, which of the following allocates CPU and memory sources to virtual machines? Remember, we said this means this, and also this means that, isn't it? Do you remember?
Yes.
Yes.
True, yes.
Yes.
It's part of the kernel module, yes.
Yes, yes. So we said this means this, all this means that, okay? And when it comes to multiple choice questions in Huawei, you must get all the answers which are correct. If you get one correct and the other one wrong, the entire question is wrong. Actually, for most of the professional courses, that's the marking criteria, okay? So as you look at the question, read through, and I would actually prefer that you use the elimination method, okay? Ask yourself, does the guest operating system allocate CPU and memory sources to the virtual machines? True or false?
False.
It is false, so we eliminate this one out. We also ask ourselves questions. Does the virtual machine monitor allocate CPU and memory sources to the virtual machines? The answer is true, isn't it? So we qualify that one. Does the hypervisor allocate? It is true. Does the host operating system allocate? It is false, so we disqualify that one as well. Okay, so it will leave us with two answers here. Okay? I hope I'm clear. Much as I'm giving you content, but I also try my level best to prepare you for the final exam. And that's one of the reasons why my students,
No, I've not sent you.
or why I have a high passing rate. Because much as I'm also focusing on the content, but I'm also focusing on you certifying, because I mean, it hurts me for a student to spend 2 weeks of attending lectures, and simply because they're not well prepared, they end up not hitting the pass mark, and yet they know everything. So I try my level best to make sure that I prepare you to the best of my ability. And if you follow my guidelines or what I say, trust me, there's no way you'll not ace that paper. And I'm saying ace, not because you just pass, but you excel. So let us look at this question here. Number 2, all right? Number 2 is saying all open source virtualization technologies are type 1 virtualization, while all closed source.
I posted it inside there.
You posted what?
Yeah, it is false.
Yeah, okay, you didn't even wait. Okay, it is. Okay. All right. Why is it false?
In fact, it's the opposite.
It is the opposite? You are sure that all closed open source are type 1?
No, it's not the opposite.
No, it's not opposite.
No, it's not, because for Huawei FusionSphere we have, it can either be type 1 or type 2.
Yeah.
Okay. And we already know that we have open source virtualization technologies which are not type 1. True or false? Like KVM.
True. Yeah.
KVM is open source, but it is not type 1. So already the entire statement is false. So I also try, that's why these questions now make a lot of sense to me, because I try my level best to prepare you for the questions. I've seen them over and over again. So I at least somehow know how you should be well prepared to take on these questions. Okay, so that brings us to the end of this chapter. And this chapter provided us with the basic knowledge about computer virtualization, include CPU, and I repeat basic, so you can go ahead. There's a word basic here. You can go ahead and read more if you want to, but just the basic knowledge about computer virtualization, including CPU, memory, and input and output virtualization. It also introduced us to open source virtualization technology by using KVM as an example, and also to commercial products by using FusionSphere as an example. Okay, so those are the recommendations, and thank you for attending that chapter. But we have about 35 minutes to 8. I feel like we should use them and go through the first chapter of chapter 3. Okay. All right, so let us look at chapter 3. Just a moment. Let me just stop the recording for chapter 1. Oh, sorry.